Hello, and welcome back to Learning with Lee. In today's episode, we are going to continue our discussion of binary by combining it with our earlier discussion on variables, so as that we can take a look at how variables are stored in a computer's memory. In order to continue our earlier discussion on variables, I have laid out the different data types that we covered earlier in our section on primitive data types. Now, for how these are represented in binary, I'm going to start off with the easiest one first, and that's bool, because a boolean is just a 1 or a 0 for true or false. So, it's relatively simple. As I showed earlier, you can convert from these other data types into a boolean. However, that ends up meaning that it doesn't matter what the final bit in that value is, such as in case you had an int such as 2, in which the final two numbers would be 1, 0. It doesn't matter that this final number is 0. What matters is that there is a non-zero number in that integer. So, the fact that there is a 1 means that that would be converted into true. So to move on to something a bit more complicated, we're going to take a look at these three data types up here, the short, int, and the long. And all of these are stored in the same way in memory. They just have different numbers of bits representing them. And I believe you can understand, given our previous lecture yesterday, as to why that is. And that's because, let's first deal with this in decimal just as a good reminder. In a single digit, so, something 0 through 9, the number of things I can store in there there are 10 to the 1 possible numbers that can be in there. As soon as I add in a second digit over here, this becomes 10 to the 2. And this keeps going the more digits I add. So another way of representing that is this is 10 to the, let's just go over here, 10 to the n, where n is the total number of digits that I have available to myself. And the reason why it's 10 down here is that is because I'm in decimal notation, and that's because before I add in a new digit, I can store 10 values here. In binary, you can only store 2 values of either 0 or 1 before you need a new digit, so it is 2 to the n. So if I say something is 32 bits long, that means that the maximum number of numbers that piece of memory can store is 2 to the n, where in this case here, since it's 32 bits, n is equal to 32. There's that. So, you can understand now why if, say, an int is a 32-bit number, a short's a 16-bit number, and a long is a 64-bit number, why there happens to be an important distinction between those bit counts. And that's because if you need to store a really large number, you're going to want to use a larger data type. But if you know for a fact the largest number you're ever going to deal with is no larger than 2 to the 16, it makes more sense programmatically to use a short then, since that'll be more memory efficient. And it can be a bit more efficient, though depending on how your CPU is, it might be more efficient to actually have things in whatever type your CPU is. So if you have a 32-bit CPU, it makes most sense typically to have things in an integer, because that should typically correspond to what your CPU is. If you have a 32-bit CPU, typically it's going to be an int. Though we'll get into ways in which you can expressly say what type of integer you want, whether you want it to be 16 bits, 32 bits, 64 bits, etc. later on. But for now, that's the major difference between all of those. In order to take a look at how these are actually considered in binary, let's consider some ways in which you could actually represent a number in binary. We've already gone over converting between binary and decimal, so you can understand that we can store numbers in there just by converting from one base to another. But let's say that I want to signify that some number, let's just, for simplicity's sake right now, we're going to go with, let's go with 6. And the reason this is 6, just as a reminder, is that this one here is 2 to the 2, and this one here is 2 to the 1, and this is what it gets multiplied by. And I somewhat made that a bit confusing yesterday, is that because this one here is the first digit, there's no zeros after it. So it's 2 to the 0. Just like in decimal, your first digit would be, in case you were to say, okay, this time is a certain amount, would be times 10 to the 0, because it would still wind up in the same digit spot. So in this case here, we've got 4 plus 2, 6. Now, let's say that I want to represent -6, and for this purposes, I'm going to say that we have an 8-bit number, so I'm just going to prepend a few zeros onto here. So we're going to take a look at it. Okay, so with that, what we can do is, what are some different ways we can do it? And these are all ways people have considered. One way, just assign one bit the purpose of being your sign bit. So whether something is positive or negative is determined by this bit over here. So if it's 0, it could be positive. If it's 1, it's negative. That's something people have suggested. Another thing that has been suggested and is known as one's complement is, let's say that I want to do -4. The way in which you do that for one's complement is you just flip the bits, in which you go, okay, 0, 0, 1, and do that, which still effectively leaves this bit here as the sign bit. Now, there's a fundamental problem with doing that sort of a complementary notation, and that's that for something like 0. Let's take a look at what happens, because 0 just is going to be 8 zeros in a row, but now you have the option of either having that, or 1 with all of these zeros after it, or 1 with a whole bunch of 1s after it, and that just would be -0. So in each of those cases, you're basically giving up a single number out of the total number of values that yours can have, because you'll end up having either positive or -0, which, since 0 doesn't have a sign, doesn't necessarily make the most sense. Computer scientists in the early days, because of the space limitations and the like, were really bothered by this, and they came up with a way of handling this, known as 2's complement. As you might guess, it's based upon 1's complement, in which you go, okay, I'm going to flip these bits here, get 0 here, 0 here, 1 here. However, what 2's complement does is then, beyond just flipping the bits, you then add in an additional 1. So it goes, okay, let's add in an additional 1. This still is 0. I add in 1, carry it over, and I get this out. So this one here would be the 1's complement, and this one here would be the 2's complement. And the major value for this is that, okay, let's continue this on logically. I've just flipped this over into 1's complement form, in which it's a whole bunch of 1s. Then if I add 1, this one's going to go to 0. I'm going to carry the 1. This one's going to go to 0, and so on and so forth. And what happens at the end here is somewhat known as an overflow issue, in terms of the fact that you effectively would be having this 1 out here, but you can't store it in memory, so it just disappears. And technically there are overflow issues where the memory that's overflowing isn't disappearing, and that's a different type, but in this case here, there's a bit of memory loss by doing that, but it allows you then to basically go, there is only a single 0, and it frees up one additional integer for you to actually be able to store in this piece of memory. So let's quickly go over a couple of examples to help deal with some of the more interesting aspects of 2's complement notation. The first thing is that when we go from 1 to -1 here, because you flip all these zeros, this becomes a 0, but then you add 1 to it, and it becomes this, then you can also reverse the process by doing the exact same thing. So it's a single algorithm, works both ways, and you just go, okay, flip all of these bits, convert everything to a 0, and then we add 1 to it, because this one here would have been a 0, and we get back out what we started with. So let's say that I have this larger, more complicated negative number here that's not as easy to figure out what it actually is in decimal. There are a couple ways you can go about it. The first is to just follow through 2's complement of flipping the bits, then adding 1 to it. So you go through this, what you'll notice is that these two, since they were both zeros, you'd add in the 1, after these get converted to that, and then this one here would get converted to a 1. And then you go through as before, and you go, okay, this one's 2 to the 0, 2 to the 1, you have 2 to the 2 here, 2 to the 3, and over here, 4, 5, and 6. And you go, okay, here's 2 to the 6, add all those up, and that gives you the positive equivalent. Alternatively, what you can do is you can go, okay, this bit here is 2 to the 7. So I'm just going to do this over here. We got 2 to the 7. Now I'm going to subtract from that the sum of these bits, similar to what I did here, is though they were a positive number. So in this case here, we have, and it'll be minus 2 to the 2, plus, and then in here we have minus 2 to the 4, and finally 2 to the 5. I don't expect you to have all these memorized in terms of what these are, but 2 to the 7 is 128. Whoops. 2 to the 2 is fairly obviously 4. 2 to the 4 is 16. And 2 to the 5 is 32. So, what you then have here is effectively 52 coming out of 128, and so you end up getting 76 for your result. Now, if we take a look over here, what we have is we've got 64 plus then 8 and then 4. So the 4 brings us up to 68, the 8 brings it up to 76, and as you can see, the two numbers we have out match. So to quickly go back over what those two styles are, the first happens to be you just do 2's complement and then you repeat the same process of converting from binary to decimal that we did yesterday. And the other one is that you take this bit and you subtract these bits and then you prepend the negation operator in order to say that it's a negative number. But really that's the two main ways of figuring out what a negative number in 2's complement happens to be. The one other thing you might have noticed about 2's complement is that there's actually more negative numbers than there are positive numbers, because 0 happens to be neither positive nor negative, but for the purposes of this, it is considered a positive number, because its sign bit is 0. So while technically that whole sign bit idea that I mentioned earlier isn't exactly what we're doing, it still matters significantly, and it still makes things very efficient in terms of checking if something is negative, because you just check whether this bit here is 1 or 0. And this is the same for any of these. There also happen to be what are known as unsigned shorts, unsigned longs, unsigned ints, and these basically go, we don't have a sign bit. We just have a series of bits that define a positive integer. So something such as, if I were to remove this here, and just focus on this top number, what this happens to be is that we go through and we do the exact same thing we did yesterday in terms of going, okay, this one times 2 to the 7, and once again down the line here, so 2 to the 5, 2 to the 4, and 2 to the 2. And the major thing about this is that it'll only give us positive numbers. And what you wind up with is, in this case here, since we have 8 bits, we have 2 to the 8 possibilities, and the largest number that you can store in here is 2 to the 8 minus 1, because of the fact that 0 is taking up one of these 2 to the 8s. If we didn't have 0, then we could get rid of this because our largest number would be exactly 2 to the 8. But since we do have 0, we stop at 255 rather than 256. Or, in the event that it's in the event it's a signed integer, we then go from, okay, positive 2 to the 7 minus 1, because 0 is being counted as a positive, and this happens to be our maximum. I'm just going to write down max over here, and then our minimum happens to be negative 2 to the 7, because we're allowing it to use all of these 7 bits in order to do that. So, in an 8-bit unsigned int, you wind up with going from 0 to 255. In an 8-bit signed int, you go from negative 128 to positive 127. Unfortunately, our conversation on this has drawn on a bit long. I hope that you can spend a bit of time practicing and experimenting around with 2's complement on your own, just so that you can understand what it is and why it's used. And we'll be moving on to floats and doubles tomorrow, so as that we can take a look at how those are stored in memory. Thank you very much for watching. I hope you have a wonderful day.